In this video, we will discuss about Kirchhoff's law of radiation. We all know a black body is a very good absorber of radiation as well as a very good emitter of radiation. Kirchhoff in 1859 from his various experimental observation gave this law, and by his statement the ratio of the emissive power to the absorptive power for any given wavelength at a given temperature is same for all substances, and this ratio is equal to the emissive power of a perfectly black body at that temperature. So this is the statement given by Kirchhoff. Now let us find a proof for this. For this, let us take a enclosure which is heated uniformly and maintained at a temperature T. And let us introduce a body inside that enclosure. And the radiation within these enclosures are independent of the nature of the walls of the enclosure as well as of the presence of the body. So, within the enclosure, let dq be the amount of heat energy lying within the wavelength lambda and lambda plus d lambda falls on the body of unit area of the surface per second. So let us A lambda be the absorptive power of a body which is kept inside the enclosure. So the total energy absorbed by the body will be equal to A lambda into dq. See, dq is the total amount of energy falling on the body per unit area per second, and A lambda is the absorptive power. So the total heat energy absorbed by the surface per second is equal to A lambda dq. So the remaining energy can be computed as dq minus A lambda dq. So this remaining energy, okay, so let us take dq outside. So within that you will have 1 minus A lambda. This rest of the energy is emitted to the enclosure either by means of reflection or transmission or by both the means. Let us take E lambda to be the emissive power of the body which is kept inside the enclosure, and the amount of energy emitted by the body of the wavelength lying between lambda and lambda plus d lambda under the same conditions of temperature is E lambda into d lambda. So the total energy given out per second per unit area of the surface is dq into 1 minus A lambda. This factor comes by the energy which is given by means of a reflection or transmission plus E lambda and d lambda. The body which is kept inside the enclosure is in the thermal equilibrium with the enclosure. So the energy which is received by it must be equal to the amount of energy given out by the body. So that means the amount of energy it is received from the enclosure must be equal to that amount of energy given to the enclosure. So at thermal equilibrium, the amount of energy which falls on the body dq will be equal to, which is emitted by it, dq into 1 minus A lambda plus E lambda d lambda. So this dq lambda can be taken inside. So dq is equal to dq minus A lambda dq plus E lambda d lambda. So on both the hands we have dq, which gets cancelled. We get minus A lambda dq plus E lambda d lambda. So taking to the other side, we get A lambda dq is equal to E lambda d lambda. And for a perfectly black body, this absorptive power A lambda is equal to 1. And this E lambda will have the maximum value. So we can write E lambda is equal to capital E lambda. So the equation 1 can be modified as dq is equal to E lambda into 1 minus A lambda dq plus E lambda d lambda. So taking to the other side, we get A lambda dq is equal to E lambda d lambda. And for a perfectly black body, this absorptive power A lambda is equal to 1. And this E lambda will have the maximum value. So we can write E lambda is equal to capital E lambda. So the equation 1 can be modified as dq is equal to E lambda into d lambda. Now let us substitute this equation 2 in equation 1, which is A lambda dq into E lambda d lambda. In place of dq, we are writing A lambda into E lambda d lambda equal to E lambda into d lambda. So this d lambda and d lambda will get cancelled. We get A lambda capital E lambda is equal to small e lambda, or this capital E lambda is equal to E lambda divided by A lambda. So this capital E lambda stands for the emissive power of a perfectly black body, so which is equal to the ratio of the emissive power to the absorptive power of a body. So this is simply nothing but this is the statement of the Kirchhoff's law. So we have proved the Kirchhoff's law. The Kirchhoff's has proved this only for the bodies which is kept inside a uniformly maintained temperature, maintained enclosure. But the emissive power and absorptive powers depend only on the nature of the body, not on its surroundings. So this Kirchhoff's law holds good under all conditions for all wavelengths of heat radiations. And this capital E lambda, that is the emissive power of a black body, is a perfectly black body is a constant. This emissive power, if in case if E lambda is large, definitely A lambda is also large. If E lambda is very small, and A lambda will also be small. So which shows that good emitters are also good absorbers. So let us discuss the chief applications of Kirchhoff's law. So Kirchhoff's law explained that good absorbers are very good emitters of heat radiations. If a body absorbs radiations of particular wavelength strongly, it also emits the same radiations strongly. So for example, the sodium D1 and D2 lines of wavelength of 5890 angstrom and 5896 angstrom, these absorption lines emits the same wavelength when they are kept at a temperature above it. Then the origin of the Fraunhofer dark lines from the solar spectrum is also well explained by Kirchhoff's law, and nature and origin of characteristic spectra of each elements or atoms are also well explained by Kirchhoff's law.